Hello, this is Jack Jackson. In this video, we're going to be talking about how to find integrals in polar coordinates, specifically to find some areas in polar coordinates. So the question is, how do we compute the area inside a region whose boundary is given by a function in polar coordinates? So for example, what is the area enclosed by the cardioid r equals 1 plus sine of t? Of course, a good place to start would be to graph this, which I've done here using GeoGebra, and you can see the graph there, and we can look at the inside of this. So we're looking at the inside of this curve here. Well, how do we do this? Well, the basic idea of integration is to slice something up into smaller pieces. Typically, in rectangular coordinates, we use rectangles. Well, in polar coordinates, we're going to use little polar slices, which are actually circular sectors. So one slice would look something like this region right here. So we come out from the origin to a point on the curve, and well, we're trying to approximate the area of between, say, theta equals alpha and theta equals beta of that curve, and the way we do it is approximate that with the circular sector. So we go out some point in between the ends of this. We could use theta equals alpha or theta equals beta or any theta in between. Here I've used one roughly halfway in between the two, and we go out and find the curve there and find that r value, which is going to be the radius of our little circular sector slice. Then we just find the area of that sector. Well, let's remember that the area of a sector is proportional to that central angle theta in radians. So the area of the sector is to pi r squared, the area of the full circle, as theta, this angle here, or delta theta here, is to the full angle going all the way around the circle, which is 2 pi. Multiplying both sides by pi r squared, the pi's cancel, and we have 1/2 r squared theta. Yeah, the pi's cancel. So the area of that sector is 1/2 r squared times that central angle theta. Or if we think of this as one particular slice, like the kth slice, then we have an r sub k for that slice. That particular r sub k is that length, that radius. And then we have that delta theta, which is delta theta sub k, the delta theta for that kth slice. And this is the area of that kth slice. So basically what we want to do is to take our entire region there and break it up into a bunch of little slices, each of which is going to be approximated by a circular sector. And then we add those up. So the area approximation would be a Riemann sum. A sub n is the sum from k equals 1 to n of 1/2 r of that theta sub k squared times the delta theta sub k. Of course, r sub k is just r of some theta sub k. Now, what are our restrictions here? Well, the delta theta is the angle, the central angle of each of the kth slice, and the r of theta sub k is an r of some theta between the two sides of the slice. So we have a theta 1 here and a theta 2 here. In between those, well, we have say an alpha and a beta here. In between those two is your theta for that kth slice. Take the r value there. Now this picture over here uses all the delta thetas the same. It's not absolutely necessary, but like we did with rectangles in Riemann sums back in Calculus 1, it's often useful to let them be the same just to make it easier, but it's not absolutely required. This one is using like a midpoint approximation where we're using the theta exactly in the middle of the two thetas here on the edge of the slice, and we're using that to find the value here. But again, that's not absolutely necessary. We could have chosen any of these r values from here all the way out to here for this particular slice. But anyway, the R value is given by that formula that determines this curve. Now, we take the limit of this as these slices go to infinity, and we have have the integral. And so here you can see more and more slices. It's getting closer and closer to the actual area. So the area is the limit as n goes to infinity of the sum from k equals 1 to n of 1/2 r of the theta sub k square delta theta sub k. Okay, when you take this limit, what happens? This delta theta becomes d theta. We drop the subscript on the k, and we put our limits. The sum here, this s, the Greek s, the Greek sigma, becomes this long skinny s, our integral sign, and we're summing from some theta 1 to theta 2, and then we do 1/2 of that. Okay, which I could factor out front of bring out front of the integral, or I could leave it inside, whichever suits me the best. Okay, these pictures here are from a GeoGebra app created by Tim Brzezinski, and he makes some very good apps, so I'm going to use that here. And in fact, let me show you that. So in this app, you can put in your formula right here, which we have in 1 plus sine of t. T is going from 0 to 2 pi. That will trace all the way around this one time. And actually it starts right here at 0, goes all the way around here, and then back to here in one tracing from 0 to 2 pi. And I can set those either by typing them in or using the sliders. Here we've got 12 sectors that you can see, and here is approximately what the integral is. But you can see this starting as we go through here, and just add more and more sectors. That is 12 sectors. You may count them and say, oh, I only see 10 there. It's because the 2 sectors right here, this little part right here, are only really, really small. But in any event, we can add more and more and more sectors, and we're getting closer and closer to the actual area that we're looking for. And you can kind of see this limit process in action here. As we slide this slider across, we're getting more and more pieces. And the approximation should be getting closer and closer to the actual integral as we take that limit. We're taking the limit of that Riemann sum. So there's 200 pieces there. It looks very, very, very close. So how can we find this value exactly? Well, here's the screen, the thing that we just saw. But let's actually set up this. Since we have the formula, we're finding r equals 1 plus sine of theta. And that's the formula there. So it's 1/2 r squared d theta. So we put our formula for r there. And if we go from 0 to 2 pi, we trace all the way around this once. So that should tell us the area inside. So let's just work this out. Squaring this out, basically FOIL, square the first term, square the last term, multiply and double for the middle term. I'm going to go ahead and distribute the 1/2 in and break this into 3 integrals. So I have the integral of 1/2 d theta, the integral of sine theta, and 1/2 the integral of sine square theta. Now sine square theta, you remember from calculus 2 that what we need to do is apply an identity to make that work out to be something we can find an antiderivative for. And that identity is sine square of theta is 1/2 times parentheses 1 minus cosine of twice the angle 2 theta. And I've just taken the limits off here, say find those antiderivatives and evaluate from 0 to 2 pi at the end. Okay? Alright, so what happened here? Distribute right here, 1/2 times 1/2 is 1/4. So this is 1/4 d theta plus 1/2 d theta is 3/4 d theta. So I can put the 3/4 out front and the d theta. So that's this term plus the first part of this one here. We still got our sine theta here. And what's left here is then 1/4 minus 1/4 cosine of 2 theta. Cosine of 2 theta, if I let u be 2 theta, then du is 2 d theta. It's okay to stick a 2 here if I balance by another 1/2. So we got a half here, and another 1/2 multiplied together makes 1/8. And the minus there makes it minus 1/8. Alright, so let's go ahead and figure out what's going on here. The antiderivative d theta is just theta. The antiderivative for sine of theta, d theta, would just be minus cosine of theta. And the antiderivative here, we got the minus 1/8 here. It is cosine u, du is just sine of u. That should be a 1/8. Okay, we got that fixed. Okay, now we evaluate now from 0 to 2 pi, which means, of course, take this whole thing, plug in 2 pi everywhere we see a theta, minus the whole thing with the 0 everywhere we see a theta. So here it is here, just with a 2 pi, replace a theta there, there, and there, minus, don't forget your parentheses here, everywhere we see a theta, here, here, and here, we put zeros here. Okay, so 3/4 times 2 pi is, let's see, a 2 cancels, so that's 3 pi, or 3/2 pi, or 3 pi over 2. Cosine of 2 pi is 1, so here we have minus 1. This is sine of 4 pi, which is 0. This is 0. Cosine of 0 is 1, so that's minus 1. That minus makes it plus 1. And sine, this 2 times 0 is 0. Sine of that's 0, so this last part is 0. The 1 plus the negative 1 cancels out. All those zeros are gone. So it's just 3/2 pi, or 3 pi over 2, which is approximately 4.7124. And here is the approximation there at the end and the exact value from TI Inspire CAS. Okay? So, once again, the area in polar coordinates is just 1/2 the integral of r squared d theta for your appropriate theta limits where it traces the part of the curve you're going to find inside of it one time. Alright, now it's time for you to try one. Find the area inside one leaf or petal of the rose curve r equals 5 sine of 4t. Okay, so the first thing you want to do is get a graph of this. And you'd really like to be able to get a graph where you only go from for one petal. So you could maybe use your graphing calculator to help you with this, or some computer software, and see if you could graph this. We'll get an 8-leaf rose here, and we only want one piece of it. Okay, so see if you can graph that yourself. Come back when you think you have it. Press pause now. Okay, so here's the full 8-leaf rose that you see in gray here, but the red part is just one particular leaf. You could have picked any one of them. And if we want to graph one leaf one time, here I started from 0, which starts at the origin, and it goes out here, and it comes back, and it turns out that happens at exactly from 0 to power over 4. If you use your graphing utility, and you tell it to only start at 0 and then stop at power over 4, you should get just this one leaf graph, and that will tell you that you've picked the right theta range. So those are going to be your limits on your integral. Now set up the appropriate integral to get the area inside this one leaf. When you think you've got it done, come back. Press pause now. Did you get this? The area is 1/2 the integral from the lower theta to the upper theta of r squared d theta. Of course, r is given by our formula, 5 sine of 4 theta. Here, sometimes I had t where I meant to have theta here, so I fixed that, so it has 4 theta there. So 5 sine of 4 theta is our formula. We square that. integrate with respect to theta. Theta is going to run from 0 to the power of 4, which traces that leaf exactly once. And remember, our formula has the 1/2 built into it. Now go ahead and work out the rest of this integral by hand and get an exact value and a decimal approximation. And then when you have that done, come back and check your work against what we're going to do in the next slide. Press pause now. Okay, well, you're back. Hopefully you were able to do this. So here's our integral we're trying to do. Squaring this, squaring 5 is 25. I can pull that out front. So I got 25 times 1/2 is 25 halves. And we got sine square of 4 theta. When we got sine square of something, we want to replace that with the identity 1/2, 1 minus cosine of twice the angle, twice 4 theta is 8 theta. I'm going to break this into two integrals. I'm going to bring the 25 times the 1/2 is 25 fourths times the integral of the just 1 d theta. Then I've got minus 25 fourths times the integral of cosine of 8 theta. But when I do the integral of cosine 8 theta, I want to let u be 8 theta, so I need an 8 d theta for du, which means I put a 1/8 out here. So 1/8 times the 1/2 times the 25 fourths is 25 fourths times 1/8 is 25 32nds. So that's here. The minus is from here. All right, so the first part, the antiderivative of d theta is just theta. And here on the second part, the antiderivative of cosine u du is sine of u being 8 theta. And then we evaluate from theta going from 0 to power of 4. So take this expression, plug in power of 4 where we see theta, minus, don't forget parentheses, plug in 0 where we have theta. Let's see. Here we get 25 pi over 16. 8 times power over 4 is 2 pi. Sine of 2 pi is 0, so that term's 0. 0 times 25 fourths is 0. This is sine of 0, so that term is 0. All these three terms go to 0. This one is just 25 pi over 16, which is approximately 4.9087. And you can see it worked out here the exact value and a decimal approximation using a TI inspired. Okay. You should be able to check that with the using this software up here, this GeoGebra applet. Let's see, our formula is 5 sine of 4t. We use t instead of theta. And we said if we went from 0 to pi over 4, that would do it one time. And yeah, there's our one region, and I believe that agrees with what we had on the other screen. So there we have it. It agrees with the approximation technique using the software there with 200 slices. Shades it pretty well. And we see that the decimal version there and the decimal version up here agree, the exact value being 25 pi over 16.